Hello, I'm Dr. David Kordowitz, and welcome to Programming. Today we're going to talk about characters and strings. This is a way of using letters and numbers in your program more the way you're used to seeing them than as mathematical operators. Characters have been represented most popularly using ASCII system. The ASCII system represents each character as an 8-bit word, meaning values 0 to 255. This system works great for American English, however, started to show problems when things became more international and we were dealing with languages that have significantly more characters. Because of this, the Unitype system was developed, or Unicode system, which can contain anywhere from 8, 16, 32, even 64 bits to represent a single letter or number. This works great for large languages such as Chinese, which can contain thousands and thousands and thousands of different characters. Now, American English is usually represented either by ASCII or by Unicode UTF-8. UTF-8 is identical to ASCII and so can be used interchangeably. If you'd like more information about ASCII and what the actual values are equal to, simply Google ASCII table. There are many available and most of them are very reliable. And the system is consistent across different computers and different devices. So let's take a look at how we can use characters in our program. The first thing we need to do is declare character. Previously, we talked about declaring variables simply by putting the data type followed by the name of the variable we want to declare. So for example, if I type car A, this is going to create a variable called A, which contains a character. Now, when I first declare it, this character is going to contain garbage, which we must repair by initializing the variable at some point prior to use. So what this does, as we talked before, is a variable is effectively a box. So when we declare it, we're going to get a box that's called A. Now what we can do is we can initialize it by assigning it equal to something. So for example, let's set it equal to B. Notice that B is in single quotes. By putting B into single quotes, that's saying that it is a single character. Now in C, C++, and similar languages, this is consistent to show individual characters, and double quotes are used to show strings. This is not how it works in MATLAB, so be aware there's going to be differences ahead. So when we do this, what happens is it takes the value B and inserts it into our character. This is really in a nutshell how individual characters work, but in most cases we want to represent not just one character, but an entire word or sentence or paragraph or something like this. For this purpose, we use what we call strings. Strings are basically character arrays. So we can declare this simply by saying something like car str by 6. So this is going to basically give us a 6-element array called str, which can hold characters. Now note that these contain absolute garbage at this point, and since we're using the C representation of strings here, we need to think for a moment how those work. Strings in C have to have something called null termination. What that means is the last letter in your string must be equal to an ASCII value of 0, which is something we call null. To make this simpler, we can go ahead and assign the entire string equal to 0. The easiest way to do this is with a command called memset. Memset is located in the string library, which you can include at the top of your program. So for example, we can do this. Here we're saying that memset str is the string obviously, to value of 0. So we're going to set the entire string to null, and we're going to say that we need to set it for 6 times, because we have 6 elements, the size of a character. Now you can use the same command in other arrays and other types. Just simply remember, instead of size of character, to change it to the size of whatever you're using. So once we're at this point, what's going to happen is immediately as soon as that line runs, your entire string will be set to 0. Now, this is kind of a boring string. It has no value. Let's load the word hello into our string. To do this, we're going to use a function called strcat, which is located in the string library. To do this, we simply put strcat str, comma hello. And what this is going to do is it's going to add hello after the first null, or actually on the first null. So it's going to replace the first bunch of characters with hello. When we do this, we're going to end up with the null still remaining at the end. This is going to tell the computer that this is the end of our string. It's really that simple. So now let's take a moment to think about, well, what happens if I want to represent a quotation mark? Well, if I put a quotation mark, that's going to end the string and cause errors. To fix this, we have something called escape characters, or escape sequences. So the standard escape sequences for C are \A, which gives you an alert, which is either a bell or a beep. As long as you have the alert function set in Windows, it'll make a sound. On older computers, it will ring the bell that is built into the onboard speaker. \B represents a backspace, so this is the deleting of a character. \E is the escape key on your keyboard. \F is form feed. \N is new line, and \R is carriage return. Now, these all three theoretically do the same thing. They bring you to a new line on your page that you're displaying on. Now, the form feed comes back from the day when we didn't have displays, but rather had printers that were printing the result. It would tell the paper that was in the printer to move up by some length, move to the next page. \N is telling it to move to a new line, and \R is from the days of typewriters to move one line, to move the paper by one line. So the thing is that the representations of these differ between operating systems. So it's important to note that something that displays correctly in Windows may not display correctly in Mac OS or Linux. And for that purpose, we have to look at where we're going to and whether we're using the Unix style return, which would be your carriage return or \R, or the Windows type return, which is \N. \N is pretty consistently working. However, when you're doing things like files and things in a Linux or Unix environment, things can get a little weird. \T represents a tab, which is great for formatting things and is used very frequently for formatting things. \V is a vertical tab. I don't think I've ever actually used that in a program. \\/ gives you a backslash because that first backslash is telling the computer that it's an escape sequence. You therefore need the second one to tell it that it's a backslash. You will see this frequently when you're working with files and things like that, where you might have backslashes in your actual text that you need to represent. \apostrophe represents an apostrophe, and \quote represents a quote. This quote here is important because normally if you put a quote, it will end your string. So let's take a look at some of the basic string functions. All but the last are located in the string.h library. So the first one is strcopy, and what that does is it copies a string from one variable, or from what we call a literal, which is having quotes around it, to a string variable. So this is a way of copying an entire string. We also have strncopy. The n in the middle means that we're taking part as opposed to taking the whole thing. There are n equivalent functions for most of the functions out there. Documentation can be found on c++.com or equivalent C reference. We then have strcat, which is concatenating strings. What that does is that places the second string on the location of the null following the string that's already in the variable. So this allows you to take two strings and add them together. We then have strncat, which allows you to do what's called appending, so you can place it anywhere in the string. You can tell it exactly where you want it, so it doesn't necessarily have to use the whole thing. It can use parts of the strings. We then have the strchr. What that does is that it'll find a character. It'll find the first time that the character occurs in your string and will return back the location of that character within your string. We have strstr, which will allow you to find a sequence of characters or string within a string. This is a useful little function if you're searching for, say, a sequence of letters that you would like to find out if they're in a list, or say you have a list of different things and you want to find whether that is in the list, whether something is in the list. We then have strlen. That'll tell you how long a string is, so it'll give you an idea of how many letters are there should you need to process this as an array of characters as opposed to as a whole string. And we have strcmp, which allows you to compare two strings. Now, strcmp can be quite confusing at first. It's using the ASCII values and comparing the difference in the ASCII values between the two strings. What you get out is the sum of the differences of the ASCII value, which can be either positive or negative or equal to 0. If the two strings are identical, it's going to be 0. Now, there are cases where you will get 0 even though they are not identical. So you need to be aware that that can happen, although normally does not happen. So this function is quite reliable. However, there are cases it can give you false positives. The last one is what we call Sprintf. It is part of what we call the Sprintf type functions, and we have a number of them that we can use. However, this one is string printf, and I'll show you how that works in the next couple of slides, but it's important to note that this is actually located in stdio.h, or the standard I/O input-output system. So when we're using sprintf, this allows us to print something into a string. So this allows us to take variables of all different types and combine them into a single string for, say, display or for output to a file or something like that. The first thing we need to do is look at the function prototype. The prototype says that the first thing we need to put in is the buffer. This buffer is your string, or as we showed before, that would be str. The format is a string which contains our formatting elements. So on a typical system, we have D or I to represent integers, U to represent unsigned integers, F to represent floating points, E to represent exponential notation, or S to represent string. Now it's important to note that float and exponential work on some Arduinos, but not all. It is very inconsistent between models which ones work and how they work exactly for those two operations. In fact, on the Circuit Playground Express, typically the float does not work. Therefore, we won't use it in the example program that we show you. It is important that you put these together, and then once this format is together, you can then take the variables that you want to represent and put them after. Those variables should be in the order that they're represented in the format string so that the computer can automatically assign the correct values to the correct locations. While this may not seem all that difficult, it can get confusing and can get odd. So for that reason, there are some additional formats that are useful. For example, we have the negative sign, which represents left align. There are ways of doing center align and right align if you need them. You can use the plus to show the positive or negative sign ahead of your variables. Normally it will show the negative, however, if it's positive, it won't show a plus. If you put a space, it'll put a space in front of positive numbers so that it's the same width as your negative numbers. If you put 0 at the beginning, it's going to give you leading zeros. So if you have 0.1 or you have, say, 1 and we say 0, if we give it a length, it'll add zeros. So it'll allow you to keep things the same length. So for example, we could say 03D. So if we have the value 1, for example, we would get 001 as the output. Because we're requiring it to be 3 in length, it is D, which means that it is a integer, and we have zeros, so it's saying we want the leading zeros. In the case here that we have %07.3f, what that's telling me is I want 7 total characters, and I want 3 of those characters to be after the decimal point. So what ends up happening if you say you have 1 in there, you're going to get 0001.000. So this allows you to control what your output looks like. So now let's take this and try it out on our Arduino Circuit Playground Express. For today's demonstration, we're going to build a device that uses the a program which uses the slider switch, which we used in the previous lesson, and the built-in temperature sensor on our Arduino Circuit Playground Express. To figure out where these connect, we're going to have to open up our pinout sheet, which we used in the previous lesson. This pinout sheet shows us that the slide switch is located in purple at 7, which means it is on a digital pin at location 7, and that our temperature sensor is located in green at A9, meaning it is on an analog pin at pin 9. When we're working in the program, we can either specify the analog pins as A9 or we can specify it just simply as 9. So what I'm going to do first is I'm going to put 2 pound define lines, pound define, and we're going to put the slider, and that is at pin 7. And then we're going to pound define temperature at pin 9. Analog pins do not require pre-configuration like digital pins do. However, the values that come out of an analog pin do need to be adjusted and scaled based on the digital to analog converter and analog to digital converter. To do this, we use the formula VFSR, or voltage full scale range, divided by 2 raised to the number of bits. Standard Arduinos usually use 10-bit analog to digital converters, and on this particular Arduino we have a 5-volt range. So we can go ahead and pound define A to F, or A to V in this case, so analog to voltage, as 5.0 divided by 2 to the 10th, which is 1024. It's important to not put semicolons at the end of the define statements because, again, they are preprocessor substitutions and would therefore put a semicolon in the middle of your line. We now need to go into our setup and set things up. So in the setup, we do need to use our serial monitor because we're going to present our results to the screen. So we're going to use serial.begin 9600 to begin our serial monitor. Again, we're going to use our while not serial to ensure that our serial monitor is connected and set correctly before executing code. We then must configure our input port for our slider. As we recall from last time, we need the pull-up resistor to guarantee that the slider will give us the correct answer. To do this, we simply do pin mode SLD, and then we use input underscore pull-up. This will set up our pull-up resistor. We now will go into our loop and begin setting things up. The first thing we need to do is declare the variables that we're going to use to store our information. To do this, we need a Boolean or an integer to store the value of our slider. In this case, let's go ahead and use a Boolean, as it's going to be a single true or false value. Let's call that SLIDE for slide. And then we're going to create ourselves a double to contain our temperature. Once we have these two variables, we're also going to need a string, which is going to be our output. To do this, we can simply use the character array style string, which we've discussed in the early. We will need an output variable where we're going to store our final result. This will be a string. Note that Arduino can handle 2 types of strings. It can handle a C style string, which is what we will be using in this course, or it can use a C++ style string, which is slightly different. We're going to actually have to use both in this case because of the fact that the %f format stream doesn't work correctly in this particular Arduino. So for this purpose, we're going to call a car output by 64, which will allow us to have up to 64 characters in the string. Simultaneously, we're going to create a string that we're going to call T output for temporary output. This is a C++ style string and will be used in the interim converting from a numeral to a string. So the first thing we need to do on each of these is to read our respective devices. So the first thing I will do is say that slide equals analog or digital read SLD. This will automatically load the slider value from the board. We now must handle how we're going to get to our temperature. So our temperature is going to equal, first we need to use our A to V and multiply it by the value that we read from the board. However, the value we read using analog read will be an integer. If we multiply or divide by integers, we will end up using integer math, which truncates all decimal points. Therefore, we need to cast our output or our input into a floating point number. To do this, we simply take double and put it in parentheses before our analog read command. What this will do is convert it to a double so that double mathematics occur in that multiplication. We will now initialize our output string using the memset command that we've discussed previously. I have my standard I/O and string libraries both included at the top of my document, so simply I'm going to use memset, the output buffer, the value I want to set it to, which is 0 for null, and then the size of the buffer. So it is going to be 64 times size of car. Now we need to take our program and take this and put it all into a final string. To do this, we're going to use Sprintf as we've discussed previously. So Sprintf is a C command, which means that the first thing we need to do is put our buffer that we're going to, which will be output. We then need to put our format string. Our slider is in Boolean, which there is no explicit format for, and thus we must use integer for that format. It'll work just fine. Now we're going to use \T to put a tab in there, and then we're going to use %s as the floating point number from the temperature has already been converted to a string. However, the string format it is in is a C++ string, and sprintf is a C command. Therefore, we're going to have to add one more thing before we can actually do the conversion. That said, we can do that in the same time as our sprintf. We need to put our variables in here, which we want to print. The first one is going to be our slider, which is located in slide. So we will put slide as our first variable. Our second variable is located in T output. As I said, T output is a C++ style string, so we can use the .c_str parentheses command to go on the end of this to convert this to a C style string. We will now go ahead and use our serial print line command to print this output to the screen. After this line, we get to the end of our loop, which will mean that all of these variables will fall out of scope, and we will begin again at the top and start over. Let's go ahead and compile this and put this onto our Arduino. We'll open our serial monitor to check this, and as you can see on the serial monitor, we now have values that are continuously changing. These values represent temperature, and if we adjust the temperature on the chip, you can see that our values will begin to change. Now, they won't show significant change because I'm simply putting my finger on this device, but you can see enough change to know that it is real. Additionally, if I flip the slider, which is there, we can see that we switch to 1 and then switch back to 0. We've built this as a string and can therefore display it. Let's say, for example, we only do want the 2 decimal places. We can go back to our code, and instead of saying temp 5, we can now say temp 2. We're going to recompile the code quickly and demonstrate that this gives us 2 points. So now you're only getting 2 decimal places. Again, if I put my finger on it, you can see that it distinctively goes up, and if I release it, it comes back down. I hope this has helped clarify how strings work in C and how strings work on your Arduino Circuit Playground Express and, well, any Arduino. I'd like to thank you for your time today and see you next time.